In this video, I'm going to walk through a rotary table sizing example using the Sigma Select software. Hi, I am Micah Studeman. Here's a quick preview. We are going to walk through sizing a rotary table for an indexing labeler machine. The rotary table specifications and motion profiles have been defined and can be loaded into the Sigma Select software to find the best motor for this application. Now let's look at this in a little more detail. At this point, I assume that you have watched the following videos that introduce you to the sizing concepts and software. Here is a visual representation of a simple indexing labeler. The machine consists of a labeler actuator and a rotary table. Cups are placed on the rotary table, then the rotary table is indexed 30 degrees, and the labeler places the label on top of the cup. Smooth motion needs to occur when indexing so the cups do not fall off the table. So what size of motor is required for the rotary table? The load characteristics and motion profile are both important. The following specifications have been obtained for sizing the rotary table. The vertical labeling motion is not being sized in this video. Looking at the rotary table, it consists of a 1/4 inch stainless steel index wheel that is 18 inches in diameter. 7.5 inches from the center of the wheel are 12 1.5 ID 2-inch OD by 1/8 inch tall cup holders. The index wheel rotates on cylindrical roller bearings connected to the machine frame. The motion profile can be broken down into two parts. One part is when the wheel indexes by 30 degrees, and the other part is when the labeling occurs. Let's start sizing the motor by opening the Sigma Select software. For this example, I will be using version 1.0.8.3. To start, I have already filled out the user information section. In the Load Editor tab, we can start filling in some required information. First of all, what mechanism are we trying to size the motor for? In this case, it will be the rotary table portion of the indexing labeler, so I will select the rotation table icon from the left side. Let's look into some of the load info. First in this section is the rotating inertia. If you remember from the servo sizing basic concepts video, the moment of inertia is a measurement of how difficult it is to change the rotating velocity of the object. In this scenario, we are looking for the inertia of the rotary table. The specification from before does not list the inertia directly, but we do know the material and dimensions. These can be used in the Inertia Calculator. The Inertia Calculator takes a user-defined model of the rotary table and calculates the inertia of the defined model. In this case, there are two parts of the rotary table that need to be modeled: the table itself, and then the 12 cup holders on the table. The cup's inertia may also need to be considered, but for this example, their impact is negligible. I'll start with the table. I'll set the label to table and set the type to cylinder. There's only one table connected to the motor, so the quantity will be 1, and there are no transmission components being used, so that will stay at the default also. From the rotary table specs, the thickness or height of the table is a 1/4 inch. This table does not have a hole in the center, so the inner diameter is 0, and the outer diameter is 18 inches. The offset is 0 because the table is rotating on its own axis. Predefined materials are available from the material dropdown. This rotary table is made out of stainless steel. The cup holders can now be modeled. I'll set the label to holders, and there will be 12 of them, so the quantity should be set to 12. From the spec sheet, the thickness of the holder is 1/8 of an inch. The inner diameter is 1.5 inches, and the outer diameter is 2 inches. The holes are offset from the center by 7.5 inches. The holder material is also stainless steel. The inertia for the rotary table has now been found. When it comes to friction force, we are looking for items in between the load and the rest of the machine that may cause constant resistance depending on the load. In the rotary table, there is a friction force occurring underneath the plate where it connects to the machine. This force is added by selecting the friction coefficient calculator and selecting cylindrical roller bearings underneath the mechanism menu. Since the rotary table is directly connected to the motor, the transmission section will not be used and can be left at the default values. Let's move on to the profile editor. Now we need to move the information from the move profile shown earlier into the profile editor. To make sure that the correct units are used, I need to set the unit options to degrees, seconds, and Newton meters. The first section is the index motion, which will be a triangular move for 0.1 seconds over 30 degrees. The last section is a dwell for 0.5 seconds. Now that the motion profile is finished, a motor can be selected from the Motor Results tab. When selecting a motor, the following 4 key sizing factors need to be taken into account: inertia ratio, speed, max torque at speed, and RMS torque at speed. For this application, let's use a direct drive motor. Direct drive motors are commonly used for rotary tables because they can handle higher inertia mismatches. I want to find a motor that satisfies all 4 of the key sizing factors. The SGM7D-38J motor fulfills all 4 of the key sizing factors according to the factor of safety ratings. The factor of safety for rated torque is 1.7, and the factor of safety for peak torque is 1.09. We like to see factor of safety greater than 1.25 for torque. This allows a buffer if the customer's specifications are a little off. The SGM7F-35D motor has higher factor of safety ratings. Let's select both of these motors for right now. In the motor detail screen, I will look at the SGM7D-38J motor first. Looking at the speed torque graph, the RMS torque value lies in the continuous region, but the peak torque is sitting just outside the intermittent region. This is because the motor cannot produce max torque at max speed. So this motor is slightly undersized for this application. So let's see if the SGM7F-35D motor will work. Looking at the speed torque graph, the RMS torque lies easily within the continuous region, and the peak torque lies in the intermittent region. The application inertia ratio is also under the motor's allowed inertia ratio. So it looks like the SGM7F-35D motor will work. But thinking back to the motion profile, we want to make sure that the index motion is smooth, so the cups do not tip over. Going back to the profile editor and clicking on the triangle move, we can adjust the jerk value to smooth out the acceleration. Let's set jerk to 25% of the XL and decel. Now we can go back to the Motor Details tab to see if the motor will still work. Looking at the speed torque graph, the RMS and peak torque values lie in their respective regions, so this motor will work. The Regeneration tab shows that an external resistor is not needed, because the power being put back on the DC bus is not overloading the DC bus. The sizing is now complete, and a sizing report can be created. The report contains all the information that was used to size the motor, along with the motor specs of the selected motor. The SGM7F-25A motor will work for running the rotary table of the indexing labeler. This concludes the rotary indexer sizing application video. For more information on Sigma Select and motor sizing, visit yaskawa.com.